Thank you very much. First of all, I'm delighted to be here, so thank you very much for the invitation. I have snuck in a few photos that I really hope Martin hasn't seen before. So what I've become particularly interested in the last few years is really looking at some of the things that Graham was talking about, really the origin of metazoa. And this, of course, is something that was very close to, well, not close to the heart of Darwin. It troubled him enormously, the fact that, as Graham mentioned, the origin of the metazoa really are very, very obscure. In Darwin's time, of course, rocks from the Cambrian onwards were teeming with life, and he was very troubled by the fact that he could find that the rocks, the preceding rocks, the Precambrian, really seemed to be devoid of life. This, of course, exercised Martin. He wrote this tremendous book, Darwin's Lost World, a few years ago. And we've heard a bit from Graham about the Ediacara biota. Often this is used as the biota that are soft-bodied. I'm particularly interested in the biota that are hard-bodied, the other Ediacara biota, those that actually give us the origin of skeletal metazoans, the origin of hard parts in the metazoa. So this is one of the many phylogenetic trees you may or may not agree with. This is just the one published by Irwin et al. Of course, the rooting of the metazoa is very controversial. These bifurcations, whether you believe them or not, extremely controversial. But what everyone agrees with, really, is that all these groups that are familiar to us, the groups we know and love, the so-called crown groups, they do all appear within just a few tens of billions of years of each other, in some place after the Precambrian-Cambrian boundary. So in other words, these crown groups appear to, very, very, almost synchronously, and that is a source of great concern. There clearly must be a considerable history in the Precambrian, but the details of this are very poorly known, and that's what I'm particularly interested in. A lot of the rise of metazoa and the rise of ecological complexity has been placed at the feet of the rise of atmospheric oxygenation. So this is just one of the many diagrams you may see suggesting that there is a causal link between the switch from anoxic, both shallow marine and deep marine waters that were anoxic, possibly euxinic in the Archaea, in other words, with a lot of free sulfur, switching to waters with increasing amounts. We don't know anything about the concentrations. It's very poorly constrained, but some amount of oxygenation in the shallow marine environment, while deep waters remained ferruginous, in other words, with a lot of free iron. And at some point here, in the Neoproterozoic, there was either stepwise or some sort of incremental increase in atmospheric oxygen that was coincident with the rise of metazoans. So a lot is being placed at the feet of oxygenation, both in terms of the successive evolution of groups with the increasing complexity, but also that ecosystems themselves started to become more and more complex. And there's a tremendous burgeoning literature on this. We know very little detail about the forcings and the feedbacks, chicken, egg. Also, the relationship between atmospheric oxygen and then the rise of actually more and more complex lifestyles, such as predation, and how that had a successive feedback on the rise of complex ecologies. So this is really a source of great interest currently. So for the past few years I've been working in Namibia, the Nama group. This interval is the approximate 10 million years or so of this, the latest part of the Precambrian. You can see the outcrops are stupendous. You can correlate sequence boundaries and maximum flooding surfaces and units for many, many hundreds of kilometers. As you can see, it's a desert. The other interest here is these beds. It's a carbonate ramp. Actually, it's mixed carbonate clastic ramp system. These beds are coincident with the first appearance of skeletal metazoa. So here you have one of these metazoa. It's Cloudina. It's a series of these little tubes. And this is found globally. It was first discovered in Namibia, but now it's been described from all over the world. You off, Martin?
I'm just going to stand at the back.
Okay. So, what we've been doing is looking at some sites in Namibia. These outcrops are over about 500 kilometers. The Nama group, so the base here is somewhere between 550 and 553 million years old. It's very, very poorly constrained, but we have various ash beds which have been dated right up and quite close to the Precambrian-Cambrian boundary here, which is perhaps about 500,000 years before the boundaries in unconformity. So we have the southern Whitputs Basin and the northern Zaris Basin. I'm going to show you some data now from 3 localities in the northern Zaris Basin. This locality is dominated by inner ramp, very shallow sediments, Onkek, slightly deeper mid-ramp setting, and then Brack is a deep water setting. So what we're trying to do is understand the distribution of oxia across a shelf-to-basin transect and correlate this with the occurrence of skeletal metazoans and their ecology. So first of all, these are the carbon isotope data. So remember, this is this inner ramp, mid-ramp, and outer ramp transect. The base here, which may or may not be diachronous, but approximately 550, and then the data just extend just beyond a dated ash bed, about 549. So it's about 4 million years worth of quite high-resolution data. So the carbon isotopes here extend right down to about -8, and then they suddenly switch more or less synchronously, as far as we can tell, to normal isotopic conditions. This switch from quite significantly negative to positive values is the well-documented Shurram-Wononka excursion. It's documented globally. It's controversial. There's a lot of debate as to whether this is a primary or a secondary diagenetic signal. I'm personally very much in the first camp, that it is a primary. Correlating it exactly, however, is slightly more problematic. But nonetheless, you can see this shift here is occurring in these 3 sites. Now, this is of particular interest because this is the big isotope shift that's thought to mark the global increase of atmospheric oxygen. It represents the oxidization of a deep buried, supposedly, a large pool of organic material. So this shift, this return to positive conditions, is supposed to mark a point where we have a significant buildup of atmospheric oxygen. And it's been proposed by many authors that this then is the point at which we see the blossoming of metazoans. So in these 3 localities, I've just marked here with this red star exactly where we find the very first skeletal metazoans in these particular localities. And you can see they are indeed post-dating this Shurram-Wononka excursion. However, that's not enough, really, to understand the detailed oxygenation story. So there are many redox geochemical methods out there, and we've just been using one developed by Poulton and Canfield, the ion speciation technique. So this was developed for use in clastics, and it's a fairly straightforward sequential extraction of different reactive ions. And all it considers is the relationship between the proportion of the highly reactive pool of ions, all these 4 sets of ion compounds, versus total ion. And if you look at this relationship, when you get a ratio less than 0.22, you can say that those sediments were deposited in the presence of dissolved oxygen in the water column, and above 0.38 in anoxic conditions. Between the 2 is ambiguous, possibly oxic or possibly anoxic. In addition, you can look at the relationship between pyrite and the highly reactive ions, and this gives you an indicator of whether you've got free sulfur or not. So below this point, we have ferruginous waters dominated by iron, and above 0.8, they were euxinic, in other words, with free sulfur. So this is a fairly simple and now extremely well-calibrated method to understand the presence or absence of oxygen in ancient sediments. Now, the slight problem is it's only just been calibrated for use in carbonates. So this is recent work of one of my PhD students, and he considered he basically calibrated this technique for use in limestones and dolomites. So this has been published in Chemical Geology, and what you can see here is a plot in squares. This is Phanerozoic anoxic sediments, Phanerozoic oxic sediments, and then a lot of modern data taken from Namibia and Black Sea, the anoxic settings, and also oxic settings. So I should say offshore Namibia, modern sediments. And you can see here quite clearly there's a very nice cutoff between anoxic data, both ancient and modern, in the filled squares versus the open squares here. And the cutoff is at 0.38. It's the same position as the upper cutoff for clastics. So we now feel confident that we can apply this technique to carbonates with a cutoff between anoxic and oxic at 0.38. The only caveat, or one of the caveats, is that it can only be applied to carbonates where there's more than 0.5 weight% iron. So you see this vertical dotted line here below this point with carbonates, both sediments and rocks that have less than 0.5 weight%. You can see here the ratio just goes wild. These are points which are actually where the modern sediments, but where we have less than 0.5 weight% iron, and you can see they're giving a false signature, a false oxic signature. So this allows us to apply calibration. There are currently insufficient Phanerozoic oxic data points, and we're working on that currently. But it gives us an initial confidence to now go back to these Nama rocks and apply this. So going back to the carbon isotope data, so here is the appearance of these first skeletal forms in these three sediments. However, and of course that confirms the tradition, the received story, if you like, the received opinion that this Shurun-Wononka excursion genuinely is showing the rise of atmospheric oxygen. However, we know that in Namibia, the very first skeletal biota appear right down here in the lower Onkek member, and in fact even slightly older in the other basin. So this carbon isotope record surely can't be a manifestation. It can't be telling us much about atmospheric oxygen. At least it's not an indication of the rise of global atmospheric oxygen. It's certainly not the case in Namibia. So then applying this ion speciation technique, and I'm sorry this is a huge amount of data, but rather messy, but what you can see here is in these three sites, so here's the cutoff at this point between oxic and anoxic. And we've plotted here data from limestone, dolomite, and clastic data, mostly from silts and mudstones. And you can see this deep water section is giving us a consistently anoxic signature. So deep waters, anoxic in both clastics and dolomites. Here we have slightly elevated TOC, which again, combined with elevated TOC, pretty elevated, up to 3 weight%. This is certainly not an oxic setting. In these two, the mid-ramp setting and the very, very shallow setting, you can see we also have evidence of very fluctuating conditions. Here we have oxic conditions shown in clastics. This is anoxic, but we have a few data points that are sitting on the line or are in the equivocal zone or indeed are in the oxic zone. Now this is particularly important because these beds with the grey symbol, these are the beds which contain skeletal biota, and in this case in situ skeletal biota. So I was very concerned when I saw this because it tells us that we clearly have evidence for anoxia either synchronously or above and below the horizons that are actually containing in situ skeletal biota. So the best explanation is that these skeletal biota are certainly living in conditions with fluctuating anoxia. And what seems to be the case is we have a deep water anoxic water mass here, and we have quite frequent upwellings into the shallow, very, very shallow inner ramp settings. However, we have skeletal biota there. So in other words, these evidence suggests that the story of rising oxygenation reaching some sort of stability, both in the shallow marine setting and the deep water marine setting, simply aren't true. We still have evidence for fluctuating anoxia coincident with the rise of skeletal metazoans. So these are just to give you an idea of the data set. We've actually now performed this for these 9 sections right across the 2 basins. So these are 5 sections in one basin, 2 in another, and you can see these are slightly higher in the succession. So the Precambrian-Cambrian boundary is up here. Black is anoxic and pale is oxic. The story is highly complex. We have evidence for these, I should say, these are inner ramp settings, these are 2 mid-ramp settings, and then this is the deep ramp. So we still have evidence for anoxia, not persistent, but episodic anoxia in the inner ramp settings right up close to the Precambrian-Cambrian boundary. Here are 2 quite distinctive anoxic sets of beds close to Precambrian-Cambrian boundary. However, what's interesting, we have areas of persistent anoxia in the mid-ramp, here and here and here. And these are all settings in which we find reefs. They're the only places in which we find reefs. So the story, it slightly feeds into Graham's idea of heterogeneity and hotspots. this terminal neoproterozoite was very, very dynamic in its distribution of oxygen. The plot thickens, so this is one of the beds that showed an anoxic signature. And when I first looked at it, I thought, well, we've just taken a bulk sample here. It's only the upper part that contains these skeletal metazoans. This lower part here, they're reworked, but on the upper surface, they're actually in situ. The lower part are classic laminated sediments. And then I realized this was quite embedded in the literature, that these early skeletal shell beds often look like this. They have a lower part, which is laminated, and an upper part of concentrated debris passing into a layer that may or may not be in situ. Very, very different from the reef settings where you have these large in situ skeletal metazoans. So I thought that the iron speciation signature is simply an average, and if we looked at the detailed micro sampling, it would indeed give us an anoxic signature here and an oxic signature here, but it didn't. This bed has a huge amount of iron in it, and it is consistently giving us anoxic signature throughout. Yeah, sorry. Oh dear. Wow. So basically, here's the upper part of the surface. These are in situ. So in other words, it tells us that this technique is too crude. It's simply giving us an oxic signature, an anoxic signature, but the lifetime of these animals is more fleeting than the diagenetic remobilization of iron. In other words, it tells us that this is another bit of evidence for even more fleeting oxygenation at this point. So ecology and redox are extremely important. So I'll just whiz through this last bit. So more recently, this is work just that we conducted in December and July this year. These ecologies are far more complex than we realise. So these are cloudina reefs. They are absolutely teeming with, this is a mass of in situ cloudina. Here it is. These are forming beds up to 20 metres thick. Here they are, preferentially dolomitised, very closely intertwining. They often form these laminated layers, or they form these stacked layers, a whole series of 10 centimetre repeating communities. Here they are in situ, very, very complex with these radiating multiple attachment sites. Little ones, big ones, loads of very early aragonite, and they all show these extraskeletal attachments here between the cloudina. They also all show a preferred orientation. So those are the larger species, these are the smaller species, and again you can see multiple attachment sites. They're attached either to thrombolite or free-growing and elevated up from the substrate. They have a preferential orientation, and we suspect this means that they are filter feeders orientated, passive filter feeders or suspension feeders orientated to nutrient-rich currents. Narmaclathus is in situ, very complex ecologies, and these forms also are cryptic. So these are cryptic cavities with these early cements. You can see here that these cloudina and Narmaclathus are attached to the ceiling of these crypts. So this ecology is extremely complicated, far more complex than we realised. These Ediacaran reefs have cryptic forms, open forms, little attached forms, and they are already showing all the characteristics of Phanerozoic reefs. So we're starting to try and unravel this signature in terms of the relationship between oxygenation and ecology, and we seem to have these reef settings which are indicative of persistent oxia, but then these settings, amazingly, in a ramp where we see a very, very opportunistic set of biotas, and they have a very, very different ecological setting. So this is really where we're going with this, trying to intertwine geochemistry with ecology to understand the to understand the ecology of the Ediacaran. Thank you.